Welcome back. This video goes deep on vector databases, the engine that makes RAG actually work. Let's get into it. TechVault runs on four internal documents: the employee handbook, the expense policy, product specs for Cloud Drive, and the Q1 all hands notes. Employees ask questions every day. How much is the phone stipend? Can I expense a standing desk? But keyword search breaks the moment the phrasing doesn't match. Someone asks about Wi Fi. The document says internet stipend. A keyword search returns nothing. That keyword mismatch is exactly the problem we are solving. Here's the code. We import two libraries, ChromaDB and sentence transformers. Don't worry about what vectors and embeddings are just yet. We'll cover both in depth later in this video. We load the model, all mini-LM L6v2. Important. Every query must use this exact same model. Use a different one and the vectors live in completely different spaces. Your search breaks. Then we spin up a ChromaDB client and create a collection. Now the document loading. We set the path to our docs directory and initialize two empty lists, one for chunks, one for IDs. For each text file, we open it and read the full contents. Then we split on double new lines, one chunk per paragraph. Chunking strategy is a topic of its own. The next video in this series goes much deeper. For now, paragraphs work fine. Each chunk and a unique ID get appended to the list. The encode call converts every chunk into 384 numbers. The four files become 247 chunks. Collection.add stores each chunk, its embedding, and its ID. ChromaDB builds the search index automatically. 247 chunks stored. The knowledge base is in. Now, let's query it. Now ask it about Wi-Fi. The question becomes a vector. Same all mini-LM L6v2 model, same vector space. That alignment is what makes the match possible. Collection.query takes that vector and returns the two closest chunks. Internet stipend, $50 per month. Wi-Fi and internet stipend share zero keywords. That was a pure semantic match. We join the results into a context string, drop it into a prompt, and hand it to any LLM. The retrieval logic doesn't care which one. So how did it find that? RAG takes a question, retrieves relevant chunks, and sends them to the LLM. Inside that retrieval step are two components doing the real work: an embedding model that converts text into numbers, and a vector database that stores and searches those numbers. Let me explain both. Starting with embeddings. An embedding is a list of numbers that captures the meaning of text. The model reads the sentence and outputs hundreds of numbers. A different sentence, similar meaning, produces similar numbers. A completely different topic, very different numbers. Same meaning, close together. Different meaning, far apart. These numbers aren't handcrafted. They come out of training on massive text datasets. The embedding model is separate from the LLM you use to answer questions. They can be completely different. Those numbers we've been talking about, each one is a dimension. Together, all the numbers form a vector, a single point in a high dimensional space. How many dimensions depends on the model. Sentence transformers uses 384. OpenAI's small embedding model uses 1536 and the large one goes up to 3072. More dimensions means more capacity to capture subtle meaning, but also more storage and compute. Here's the key property. Imagine projecting all those dimensions down to 2 so we can see them. Sentences about animals land here. Finance sentences cluster here. Tech over here. Similar meaning, same neighborhood. That's the entire foundation of vector search. So which model generates those vectors? OpenAI's embedding API. Fast, reliable, solid default if you're already in that ecosystem. Cohere for strong multilingual support. Sentence transformers runs locally. No API key, completely free. That's the one you just saw in action. Same model, same vector space, embedding your documents and your queries. None of these affect which LLM you pick for generation. The two are completely independent choices. Now, how does the database find the closest match in milliseconds? It uses cosine similarity. Picture two arrows from the same origin. The angle between them is the similarity score. Small angle, similar meaning, score near 1. Large angle, very different, score near 0. Wi Fi and internet stipend had a small angle. That's why it matched. For a million vectors, even cosine similarity 1 by 1 is too slow. So databases use approximate nearest neighbor search, ANN. The space is divided into clusters. A query navigates directly to the right neighborhood. It searches only within that cluster, slightly approximate, orders of magnitude faster. So, which databases implement this? 7 serious options right now. 3 dimensions that matter to architects: hosting model, whether it's purpose built for vectors, and what existing infrastructure you're working with. Pinecone, fully managed, zero ops, production ready on day 1. Qdrant, self hosted, written in Rust, fastest raw ANN performance. VV8, open source, hybrid search built in from the start. Milvus, built for billions of vectors, serious ML infrastructure. ChromaDB, embedded, zero config, runs inside your Python process. pgvector, vector search as a Postgres extension, no new service. Elasticsearch, full text search that added dense vector support. If you're already running it, adding vectors is low friction. Here's how they compare. Pinecone, fastest time to production, fully managed. Qdrant, if raw query speed is the hard constraint, this is the pick. VV8, most flexible self-hosted option, hybrid search included. Milvus, only worth it at genuine enterprise ML scale, operationally heavy. Elasticsearch, low friction if you're already running it. If you're not, don't start here just for RAG. pgvector, handles tens of millions of vectors before you'll feel a ceiling. For most RAG systems, that's plenty. ChromaDB, not for production, but it's the fastest path from zero to working retrieval. We're using ChromaDB for one reason: zero setup. No API keys, no Docker, no config file. It runs in the same process as your code, and the concepts transfer directly to anything else on that list. Collection.add in ChromaDB, index.upsert in Pinecone. Different syntax, same idea. Swapping the client when you're ready for production is about an hour's work. Here's a decision tree you can actually use. Start with your existing stack. On Postgres, pgvector, add the extension, done. Running Elasticsearch, add vector search, no migration needed. Starting fresh, managed or self-hosted. Managed, Pinecone, free tier is generous, zero ops. Self-hosted, what scale? Billions of vectors, ML workloads, Milvus. Speed critical production, Qdrant. Need hybrid search from day 1, VV8. Prototyping, ChromaDB. Migrate when you hit a real limit. The pipeline works, but there's an assumption underneath it. We chopped documents into chunks by paragraph and hoped the right answer landed in exactly one of them. What if the chunk is too large and the answer gets buried? What if the answer spans two adjacent chunks? What if the top result is semantically close but says something different? Next video fixes that. Document chunking is the step most RAG tutorials skip entirely, and it has more impact on retrieval quality than almost anything else. Thanks for watching. Full code is in the GitHub repo, link in the description. Subscribe so you don't miss the chunking video. It's the one that changes how you think about everything else in RAG. Find us on social. See you in part 3.